Okay, welcome everyone. I'm Todd Morrison. I'm the director of Las Vegas Observatory. Happy to welcome you here for the beginning of our third year of public talks. Before we get started, I want to tell you about a couple of upcoming events. We have two more talks scheduled this year. We have Gabriela Gonzalez from Louisiana State University. She's coming in May, and she's going to talk about LIGO, the Gravitational Wave Observatory. She's one of the scientists involved with the discoveries of the gravitational wave events, and that's going to be downtown at the Center Stage Theater. And we have Andrea Getz from UCLA. She's coming in November, and she works on the supermassive black hole that's in the center of our galaxy, the Milky Way. And she's one of the foremost experts on studying that black hole in our galaxy and understanding what its effect is on things near it and not so near it, because it's very massive. We also have Astronomy on Tap, another one of the events that we do. That's going to be on March 7th at the Matrix Bar downtown on State Street. And that's our, the theme of that Astronomy on Tap is celebrating women in science. We have two women speakers. We have Isabel Partido from UCSB, who's talking about taking pictures of exoplanets. And we have Monica Turner from our organization, Las Cumbres Observatory, who works on observing satellites and things launched into space. And her talk is called From Sputnik to Tesla. We also have an open house coming up. We ran open houses at our facility a few years ago, and we've had a lot of demand to do that again. So in March 21st, we're having an open house, and you can find out more information about that on your website if you're interested in visiting, seeing where we build the telescopes and the instruments and operate everything from. We have 21 telescopes now spread all around the world. We're operating all the time. We have a few more that we're planning to put out there over the next couple of years. We're working 24/7. We have a user community all over the world doing all different kinds of science. About tonight, we're going to have the talk by Professor Fischer. Just want to tell you what's going to happen. Then we're going to have a question and answer part of the show, and then we're going to have a reception. She'll hang around for a while and talk to you if you want to ask her further questions. And let me say a little bit about the subject that we're going to hear about tonight. I'm going to introduce her in a second, but I want to tell you why I think this is really exciting. Exoplanets, to study the planets around stars other than the sun, is a pretty new field. It's only been around about 25 years. We always thought that there were planets around other stars, but it's only the last 25 years that we've been able to detect them. We've gone from detecting the first one in the early 1990s to having several thousand that have been discovered, both from ground and from space probes. But the techniques that we use, the fact that it took so long to figure out how to detect them, and that the number has grown, and it's grown slowly at first and much faster later on, is because it's really hard to do. And the techniques that we have for discovering them, they discover sort of planets, but they're not planets like Earth. They're planets that are very massive, like Jupiter. They're planets that are orbiting close to the star, that they're going around like Mercury. It's even much harder to find planets like Earth than it is just to find planets. But amazingly enough, 25 years after the discovery of the first exoplanet, we're now beginning the second phase of work on exoplanets. And Debra, who's going to talk tonight, is one of the leaders in that because she builds instruments that allow us to detect Earth-like planets. And the techniques are much more sophisticated than the original techniques that were used to discover any planet, and particularly planets that are not like the Earth. So I find it really exciting. This is a field that of course, we personally can relate to, looking for other planets like Earth elsewhere in the galaxy. And we're about to start the most exciting part of it, where we're actually going to begin to find these other planets like Earth. Let me introduce Professor Fischer. She did her undergraduate work at the University of Iowa, and then she was in the Bay Area for quite a long time. She was at San Francisco State, got a master's. She was at UC Santa Cruz, built banana slugs, where she got her PhD. She was a postdoc at San Francisco State and at UC Berkeley, and then faculty at San Francisco State, and then Yale said, enough of this, we want her here, and she's been a professor at Yale since 2008.
Thank you so much for that lovely introduction, and thank all of you for coming out tonight. I think this is a really fun topic. I'm sorry I'm going to be up here kind of in the dark, but I'll keep my eyes out, so if you have any burning questions, just jump up and down and wave your hand. Otherwise, we'll, of course, have questions towards the end. But we wanted to keep it kind of dark because I hadn't realized that, it's just hard to see the slides. So anyway, let's get started. Okay, so as Todd said, I've been searching for exoplanets actually for my whole career. I came out of graduate school just as the first exoplanet was detected, and it's amazing to me that for 25 years has gone by. When I think about exoplanets, I think about the planets in our own solar system, and I'll often refer to a planet as a Jupiter-like planet or a Neptune-like planet. And so to me, what that means is that, Jupiter is about 317 times the mass of the Earth, 10 times the radius of the Earth. Saturn is 100 times the mass of the Earth. Neptune is 17 times the mass of the Earth. And these four planets at the sort of the end of the range here, these giants in our solar system, are really the ones that we were detecting with the observational technique that I've used for my whole life. And of course, things have changed. But really, instead of just thinking about this is the picture that we have right now, right? But as we begin to go out and look for worlds orbiting other stars, it's not going to be so easy. So this is a little bit hard to see, but I want you to keep looking at this image and tell me if you can see the planet in this image. Everybody see it? All right, all right. Some of you guys are pros, right? So just in case, I'm going to bring in a little circle right here. And of course, this is an image that was taken by the Voyager spacecraft when it was out near where Jupiter is in our solar system, looking back at the Earth. Carl Sagan lobbied NASA to please turn the spacecraft around and take a picture of the Earth. And the engineers were very nervous about doing this because, if anything went wrong, it would mean the end of the mission. The Voyager spacecraft was launched in 1977. It is still out in the outer part of the solar system, just leaving our solar system, radioing back a little signal with an intensity, a power of 2 watts. We can still receive that signal from the Voyager spacecraft. And so, when Carl Sagan, and again, I really do like to imagine what it's like, when people discover new things. That is the most exciting thing about being a scientist. And I just wonder, you can tell how inspired Carl Sagan was when he got this little picture of this pale blue dot, because he so poetically said, look again at that dot. That's here. That's us. On it, everyone you love, everyone you ever knew, every human being who ever was lived out their life on this little mote of dust suspended in a sunbeam. Okay, and this again is a picture that's taken in our solar system, just 5 times the Earth-Sun distance, right? So we're talking now about building spacecrafts. I'll get to this at the end of my talk. Telescopes in space that will be able to take images like that, but of planets orbiting stars that are very far away. So really, this is how I should be thinking of the Earth, as a little dot where if we're lucky, we'll get 4 or 10 pixels on that little dot and try to glean some information. I always like to think about this myself. I always like to start my talks out, so I hope you'll bear with me if you already know all of this. But our sun is just an ordinary star. It's one of about 400 billion stars in our Milky Way galaxy. And so a lot of times we think about all of the troubles that we have here on Earth, right? And this is our entire world. It's everything we know. But every once in a while, I think it's important to just step back and really think again about our place in space and in time. And for me, this is what motivates the whole search for exoplanets, to try and figure out, who we are and where our place is and whether or not there are creatures that are living on other worlds. So our sun is just an ordinary star, 400 billion other stars in our Milky Way galaxy. That already seems kind of small, but let me put up this picture of the moon. I'm going to take the moon away in just a little bit. I have a picture of the moon because I want to give you a sense of scale. Everybody knows how big the moon is. There's a beautiful crescent moon out tonight, by the way. You should look up when you walk out of this building. You can see the Orion constellation. And the Hubble Space Telescope pointed at this little patch of sky. You can see these the CCDs, the charge coupled devices. See if I can do something without breaking it right here, right? So those really are representative. They're the right scale. And Hubble looked at a patch of the sky near the Big Dipper. And the reason that we looked there was because astronomers thought it looked like there was nothing there, a really boring part of the sky. And so the question was, what is there in the sky when we think that there's nothing there, right? What could possibly be there if we look long enough? The Hubble Space Telescope goes around the Earth once every 92 minutes. And as it came around to this part of the sky, the shutters would open on the camera, and it would snap, snap, snap pictures until it had accumulated 3 weeks of open shutter time, right, on this little patch of the sky. So, is there going to be nothing there? Who knew, right? We asked the question. We were brave enough and bold enough to ask a question like that, very open-ended. But again, think about being one of the scientists at the Space Telescope Science Institute when the image came down and the astronomers stacked the images, co-added them so that they could see a very deep field. And what they saw in this little patch of the sky was 10,000 galaxies, okay, out beyond our Milky Way. And if you think that there's something special about that patch of the sky near the Big Dipper where we thought there was nothing, no, that's not right. Hubble has now looked at these what are called pencil beam surveys, so very deep surveys looking at other parts of the sky. The entire celestial sphere is wallpapered with this image, right? In every single direction, hundreds of billions of other galaxies, right? Which really gives this incredible sense of how tiny we are. Maybe you feel how insignificant we are. I would like to come back and challenge that idea as we go along, but it's worth thinking about. Okay, so our place in space is small, and actually our place in time is even perhaps smaller, even less significant. The universe began with a Big Bang 13.7 billion years ago. I have absolutely no idea what that number means, right? I can't relate to it. My human lifetime doesn't have a scale where I can even get my mind around that number. And so Carl Sagan again cleverly said, let's rescale 13.7 billion years to something that we all understand. We'll have a cosmic calendar. The universe begins on January 1st in this rescaled timeline. And by May, our Milky Way galaxy had formed. By August, our sun had formed, along with its whole suite of planets. By September, right, just 500 million years. So our sun formed 4.5 billion years ago. 500 million years after our sun formed, the surface of the planet was infested, right, with microbes, with single-celled organisms that persist to this day. But if you look, they dominate our world from September, October, November, December. So let's zoom in, because now I'm a little worried about where we are on this cosmic calendar. We really have to look here at this last month of December, right? The clock is about to tick over to the new year. And you can see that here's December 25th, so Christmas Eve, the dinosaurs appear, right? So we have a big problem because the dinosaurs are here for a whole cosmic week. They're here for a cosmic week. And I just wonder, what did they do with all of that time that they had here on this earth? And then where do we come in? We don't come in until much later, right? In the last 60 seconds of the year. So the earliest examples of Homo sapiens appears just a few minutes ago, right? All of human history has occurred in the last 60 seconds of the cosmic year. Technological humans have been here for a millisecond, right? And so this is where now I start to think that maybe we aren't so insignificant after all, right? The dinosaurs were there for a whole cosmic week. I think the only thing I know of that they did for us was they gave us fossil fuel so that our technology could flourish. But in the millisecond that we've been here, we figured out that the universe started with a big bang and that every atom in our body came from a star, was forged in the core of a star. So that is incredibly remarkable to me, that even though we don't occupy a big place in space or in time, there is still something really, I think, phenomenal about human beings and about their curiosity and about science, that we do this just because we want to understand the way that things work. So in the introduction, I think Todd said that, we didn't find the first exoplanet until 1995. I'm not sure. Some of us, we did think that other stars had planets, but was it 1 in 10 stars that had planets? Was it 1 in 100? I think some of us were getting worried who were working in this field, right? That astronomers have been looking for 100 years for exoplanets and had not found anything. And at a meeting in 1992, astronomers, I remember people saying, we really have to be, careful about this. Planets might not be very common. We might think they're common because we're sitting here on this planet, and, but maybe they're rare. We have to allow that as a possibility. And if planets are rare, then life is certainly rare, right? Because life flourishes on the surfaces of planets. But by the end of this year, so just when we thought it was all over, just when we thought that maybe there weren't very many planets in 1995, the first exoplanet was detected. Clinton was rising. And the thing that sort of strikes me about this cover of Time magazine is that, it's not, we found a planet, it's that this renewed our excitement about whether or not there could be life in the universe. So I saw this field where, the SETI, the Search for Extraterrestrial Intelligence, was thriving, and it was beginning to really take a huge dive. The funding for SETI had been pulled out from underneath of them, and the discovery of exoplanets opened a whole new field. And so it's been remarkable for me to see this time when, maybe we thought there weren't planets to maybe, in fact, there are planets around every star. I wanted to tell you a little bit about the technique that I use. So the method I use is called the Doppler technique. And here in this cartoon, you can see that there is a planet that's going around a star, but the star is also orbiting a common center of mass with the planet. So gravity connects a line between the star and the planet at every position, right? The star is essentially wobbling in space. And you saw, let me try and rerun that again. And what you also saw here was a spectrum of the star, right? And this spectrum is shifting back and forth, right? This is the Doppler effect, that any wave, if it's coming towards you, is going to be blue shifted, and if it's going away from you, is going to be red shifted. So this is the physics of what we're doing, but I want to tell you that we don't see the planet, we don't see the motion of the star. Usually the stars that we look at aren't visible with the naked eye. We have to have a powerful telescope. And the shift of these lines that I so blithely had, dancing back and forth, you wouldn't even see that with your eye, because the shift of these dark absorption lines is typically 1/1000th of a pixel on a CCD camera, right? And so it boggles my mind that we can use this technique, employ the laws of physics, right, to figure out that there are planets orbiting these stars. People didn't believe the first discoveries that we had. They believed our data. Our data were beautiful, but they weren't sure about our interpretation that these were really exoplanets. So it was fun to watch all of that change as well. and to see that in the years, right, so here I show the discovery of planets in Jupiter masses, big planets, going from the sort of 1990s up to here, right? And by the way, I did tell you the first planet was discovered in 1995, so you might wonder, why are these other dots here? So these are planets that, in retrospect, we realized that they actually were exoplanet discoveries, right? But at the time, no one really believed it. So from 1995, you can see a couple of things going on in this chart. First of all, there are more and more dots as time goes on. These are all discoveries with the Doppler technique. And secondly, I love this arrow because it's telling me that the mass of the planets that we're able to detect is going down. We're getting smarter, right? Our precision is improving until finally we get down to about 1.5 Earth masses. And one of my friends who was a theorist looked at this plot and said, oh, look, we just have to wait until, 2015 and we'll be finding Earths. It doesn't really work that way. I wish it did, but it means that, these are hard-won improvements in technology and in our strategy for observing planets. But we really are getting down close to finding Earth-like planets with this technique, and I guess the question is, can we do it, right? And I am, at this very minute, actually, my graduate students are at Lowell Observatory in Flagstaff, Arizona, where we're commissioning an instrument that we think will give us the precision to do this. Okay, so we want to detect small planets, rocky planets. They have water pooling on their surface. We think those are good petri dishes for life. And we also want to find planets that orbit at a distance from their host star that's often called the Goldilocks zone, right? Not too close so that it's really hot and the water steams away, not so far away that the water is frozen, but in the just right zone so that the water will pool on the surface of a rocky planet. And here you see these are different types of stars, right? Right here is the sun. These stars are more massive and bigger. These stars are less massive and smaller. And the habitable zone, right? You can think of these as like a light bulb that's on a dimmer switch. So here's our 100-watt, light bulb, and we turn up the dimmer switch until we get a higher, brighter star. And now the intensity, the energy that's coming off, it's a lot hotter near this star because it's giving off more energy, so the habitable zone moves further away. As we go down to the smallest stars that nature makes, we're turning the dimmer switch way down, right? And so for a planet, for water to be in a liquid state, the planet has to be found relatively close to its host star. Here are 3 planets in our solar system: Venus, Earth, and Mars. In some sense, any of them are pretty close. Earth is smack in the middle of the habitable zone. Is that a coincidence? I don't think so. I think that's an important clue, right? That Mars doesn't have life and Venus doesn't have life. So we're sort of right now going, and you guys may ask the question at the end, but aren't you being really narrow-minded, taking this view that life has to be like life here on Earth? And I think it's life that we recognize, right? It will be easier to find it. So this is the technique that I've been using. There is another technique that came along in the late 1990s called the transit technique, and I bet you've heard about this one. In this case, we have a star right here, and as the planet goes across the star, it blocked out some of the light. So here's a measure of the brightness of the star, and then the star dims just a little bit. And just to let you know, we don't see the planet, right? Maybe we see the shadow of the planet, but what we actually see is the brightness of the star dimming. We don't resolve the disk of the star. So you see an image, and it looks like, it looks like it could be a real picture. But this is artistic license that reproduce the thing that we're seeing. Often the star is only visible with a powerful telescope, right? And the change in brightness that we're talking about is generally less than 1/100%. And it only lasts for a few hours. So none of these techniques are easy, and yet what we have discovered is incredible. I'm sure you guys heard in the last year about the TRAPPIST-1 system. Phenomenal discovery with the transit technique, right? So here's a star, TRAPPIST-1, it's called. TRAPPIST-1 is one of those little tiny stars. It's just barely fusing hydrogen in its core. It's the size of Jupiter. It's so small, right? The size of Jupiter. But it turns out that these stars are the most common stars in our galaxy. They dominate. They're 70% of the stars in our Milky Way galaxy are low-mass M dwarfs. And here is this system that has 7 rocky planets around it. The first planets around TRAPPIST-1 were discovered in 2013, and then with more scrutiny and using space telescopes like the Spitzer spacecraft, additional planets were found. I thought I would just show you the data. I love data, right? I love to see what the actual observations look like. So here what you see is brightness measurements of TRAPPIST-1 over time, right? And just a continuous, there's a little bit of scatter that represents partly our errors, right? The scintillation from the Earth's atmosphere. And then you see every once in a while these dips in the brightness, right? And so those are caused by these transiting planets. And they've been labeled here. So this dip in the sort of a magenta pink color, it happens really regularly. It's like clockwork, right? This top diamond. That one is happening the most frequently. And that one must be planet B in the system. And then if you look in the row right below, there's a lighter pink color. Its orbital period is longer, right? That's planet C. And if you look the gold, follow the gold points, that's even a longer period. And then the brown points here. And then by the time you get to the last 3 planets, well, the last one isn't even on this plot. These two, there's one transit event. They happen to just lie right on top of each other. So we can tell the size of the planet from the depth right here. We know that see how some of these are shallow and some of these are deeper. The deeper ones are bigger. They're blocking out more of the starlight. So we get the radius, the size of the planet. And given the size, it's hard to imagine that these planets are anything but rocky. They're probably just small rocky planets. In 2009, NASA launched the Kepler spacecraft. Kepler went and was initially in an orbit where it looked at a part of the sky, right here. And you can see, we see Altair, and here's Vega, and here's Deneb. So that's the summer triangle, right? That helps you locate the part of the sky where the Kepler field is looking. Here's an array of CCDs. These are the electronic photographic plates, essentially, that are collecting data. And Kepler was staring at this part of the sky, looking at a couple 100,000 stars just 24/7, nonstop, right? And beaming the data down to the Earth. The goal of Kepler was to figure out how often stars had Earth-like planets. And let's see if Kepler succeeded. Okay, so here are the data. So you saw before the plot that I showed you with planet mass and orbital period. Now I'm showing you planet radius, because that's what the transit technique gives, an orbital period. And there are thousands of data points on this. There's also this kind of interesting slope in the data. If we were to lay down our Earth, right, at 1 year, right here, and 1 Earth radius, there it is, you can see that Kepler didn't find very many planets that are like our Earth, that orbit at this distance, right, in the habitable zone. And so so in some sense, Kepler didn't meet its goals, and yet would you call it a failure, you know? When you found thousands of planets, it's absolutely incredible. So I've bracketed here with red lines one of the most interesting types of planets that have been found, planets that are in between the size of Neptune and the size of Earth, right? We don't have any of these planets in our solar system, so we don't really know how to characterize them. There are planets that are missing here, but they're not missing from nature. They are missing because the spacecraft, first of all, detects planets that are preferentially that are closer. So there's a completeness, observational completeness issue. And then also Kepler needs to get 3 transits. Planets that are farther away have longer orbital periods. And Kepler lost 2 of its reaction wheels once it was starting to get out to sort of this region right here. So that's where the story ended, right? But what we have from Kepler is this incredible wealth of information about exoplanets. And we see a diversity in exoplanets that we just never could have imagined. Of course, we see some planets that are similar to Earth, some planets that are kind of like Neptune. But then there are these planets in between, right? And what we know is only the size of the planet. And so if you only know the size, is it a planet that's a super Earth, or is it a gaseous planet that's a mini Neptune? We don't know, right? Unless you get not just the size, but also the mass, we don't know. We can't tell the difference between these 2 types of planets. We've learned a lot, though, about how planets form and migrate. The planet one of the things that I studied in my early career was analyzing the chemical composition of host stars. And what we've learned is that the elements in the periodic table, right, that we find in the atmospheres of stars influence or certainly are correlated with the types of planets that we find. So there are some interesting clues. We're learning not just about occurrence, not just about characterization, but really about formation. We're seeing the fossil signatures of planet formation. So I'll just cut to the chase here and tell you guys that we not only went from thinking that maybe most stars didn't have planets to being able to come up with some statistics. We now know that the occurrence rate of planets, where the planets have sizes similar to the Earth, in orbits from 50 to 200 days, so that takes us out to about the orbit of Venus, right? Around sun-like stars, 33% of sun-like stars have these small rocky planets. When we get down to the M dwarfs, the low mass runts in the litter of stars, right? The ones that make up 70% of the stars in our galaxy, the occurrence rate is 54%. And typically what we see is that there's not 1, but there's 3, or there's 7, or there's some incredible number of small rocky planets orbiting the M dwarfs. So if you just went by these statistics, right, then you would say, all right, I know where I'm going to look for Earth-like planets. I'm going to look around the M dwarfs. One thing that worries us a little bit, and I don't think we should project too much, right? We don't have enough information, but it is true that if you compare a star like the Sun and one of these low-mass M dwarfs, that there's a kind of surprising difference. And the difference is in the flares that are given off by the stars. So while occasionally the Sun will have flares that are 45 times the sort of normal intensity of flares, these little M dwarfs have flares that are 100,000 times as strong, right? And what's coming off when a star flares are protons and electrons that are going at very incredible speeds, right? And so as they sweep past a planet, they're stripping off the atmosphere of the planet. So this high activity solar wind from the M dwarfs could be essentially pulling the atmosphere off of planets in the habitable zones around these low-mass M dwarf stars. Nevertheless, I think the jury is out. I think we owe it to ourselves to actually keep looking for more of these systems like TRAPPIST. One of the things that I didn't mention is that, our sun is 4.5 billion years. It will live for another 4.5 billion years, right? That means our sun lasts for 9 or 10 billion years. These M dwarfs last for 125, 200 billion years, right? They've been around since the formation of the universe. None of them have evolved, right? They're still in their normal hydrogen-burning state. And so I think if there is life on the TRAPPIST system, they'll be there for 100 billion years. And they'll be looking at this star, the sun, right, with its planets going around it. And as the star becomes a goes through its giant phase, maybe we'll radio out to the TRAPPIST system saying, come and help us. And, and they'll be there, wow, I don't know, man. We're going to go over there and... But they will, it gives the potential for the evolution of life. It gives that process a really long time to work. So all these pink dots, many of the pink dots are exoplanets that I found or with my team found. The blue dots are planets that were found by ground-based transit surveys, right? We were always pretty proud that every year we found more planets than the year before. Then along came Kepler, right? That's what you call a game changer, right? So Kepler added all of these yellow points here. And with Kepler, we learned that, in fact, almost every star in the galaxy has planets, right? Almost every star. And generally, there's a whole architecture, several planets. That means I told you there were 400 billion stars in the Milky Way galaxy. So you can multiply that number by, 5 or 10. That's how many planets there are in our Milky Way galaxy. It's quite a staggering number. And it's amazing in my career to be able to go from not knowing if any stars had planets to realizing that planets are common, right? The thing that we're missing so far are the Earth analogs. Where are the planets? Where's Earth 2.0? And it's not because they're not there. It seems very clear to me that, these are the hardest planets to find, and they've just slipped through our fishing nets so far. That's what's going to change in the next decade. And as that changes, we're going to be able to look at those planets and search for life. I think we're going to be in a situation, I remember in 1992 when an astronomer said, well, gee, we have been looking for a long time and we haven't found planets. Maybe they're not there, right? And to this point now where we say, oh, no, planets are a dime a dozen. They're around every star, right? What happens? How do we as humans deal with this idea that, in fact, the first biosignatures are going to be incredible news, front page of the New York Times, and then pretty soon it'll be hundreds of planets that have life, and we'll start to figure out what the zoo of life looks like on other worlds. I think that's what's going to happen. I've come full circle from thinking that life must be really rare to thinking that life was inevitable on this planet. It was not a freak accident. It was the outcome of the chemistry and the chemical equilibrium on this planet. And if that is the case, then it means that life springs up on other worlds as well. Okay, so I have to tell you a little bit more about the work. So I showed you data for transits. This is data much of this data I took on a star called Tau Ceti on Mount Hamilton above San Jose at the Lick Observatory. And this star was our poster child for a star that was really well behaved, and it was as quiet as you could get, and we like to show our data and say, look how good we are. And yet I want you to look at this scale. So this shows you the velocity of the star over time. And although this is in Julian dates, this spans something like 15 years of my life running up and down the observatory. And you can see that the error bars that we have are about 13 or 14 meters per second, or the scatter in our data is about 13 or 14 meters per second. Our error bars are about 5 meters per second. So to show you this data, I have to put it on a scale from minus 100 to 100. I guess if I really wanted it to look good, I would change it to minus 500 to 500, right? And then it would look like everything is really good. Yeah. So we built a spectrograph. My team built a spectrograph, which is operating now in Chile, the Chiron spectrograph. And this is that same star, Tau Ceti. Now I've changed the scale from minus 100 to 100 to minus 30 to 30. Our scatter and our error bars have come way down, right? And so a lot of this is improvement in the instrument and also in the observational technique. Just as a reminder, I'll show you the old data on the same scale, right? And you can see how much better this looks. And I can tell you that we are trying to go one more order of magnitude, another factor of 5-ish or 10-ish improvement in our precision in the future. That means that we have to work really hard. I make my team work very fast. They come in all day and they run around like this constantly. So this was the second spectrograph we built. This spectrograph is actually in operation in Lithuania, amazingly enough. And the instrument that we just finished is called Express. So we built Chiron at Cerro Tololo in Chile, the View spectrograph in Lithuania, and we just finished Express, which is being commissioned now at the Lowell Observatory. So here are some kind of fun pictures. This is a vacuum chamber that weighs 3 tons. So the DCT staff like to, look like they're real strong guys. Then also my team said, okay, Debra, go down and pose with a wrench and pretend like you do something besides yell at us about the budget. So I did that. But really, a guy I give all the credit to, Colby Jurgensen, is the optical designer for the instrument. And here's a picture of the spectrograph from last week. We yesterday put the sides of the vacuum enclosure on, and we are now pumping it down. I think it's quite beautiful. I don't know. But this will be an incredibly stable spectrograph, and we're really excited to find out if we can boost our precision by a factor of 10. If we can, then the Earths are going to come rolling out around nearby stars. And I like this because it gives us the names and the addresses of these small rocky planets for future space missions, which I'm also really interested in. The project that we're hoping that we will carry out with Express is called the Search for 100 Earths. It's true that there are now more than 4,000 exoplanets known, mostly because of the transits, but we don't really know what any of them look like. We don't have mass measurements for many of them. We don't know what their densities are. And so we would like to change this. One of the things that we need are more powerful telescopes, right? If you ask an astronomer what they want, it's always a bigger telescope, more glass. So here's a picture. See if any of you know what this picture is of. Galileo, right, telescope, a replica of the Galileo telescope inside of a shuttle. And if you look through the window, that was servicing the Hubble Space Telescope, right? So imagine like Galileo with this telescope, how proud he must have felt to be able to look at Jupiter and resolve the moons of Jupiter and see Venus, that, Venus went through phases, and understand that that's because of its orbit. But what a difference we have from the Hubble Space Telescope, one of the first pictures I showed you, right, of that 10,000 galaxies in that tiny little beam on the sky. So, we need bigger telescopes always. And what NASA has planned is going from, we have ground-based telescopes, we have 30-meter class telescopes that are being designed and built right now. We've gone from Hubble, the Spitzer spacecraft, to Kepler, which I told you about, that was just launched and gave us all those incredible discoveries. In mid-April, so like 6 weeks from now, something like that, TESS is supposed to launch, and TESS will return an incredible bounty of exoplanets, perhaps beyond Kepler. And the exciting thing is that TESS, instead of staring at one part of the sky, will be scanning the sky, looking at all of the closest stars. And then finally, the James Webb Space Telescope, which is now slated to launch in 2019. And with James Webb, we're hoping that we're actually going to start to look at atmospheres of exoplanets. So here's the kind of thing that a spectrum can tell us, right? This is a spectrum, so this is the intensity of light going from blue wavelengths to red wavelengths. And here you see that the blue wavelengths are rising. That's because of, this is a real spectrum of the Earth, I should say, right? And so on the Earth, we have this blue sky, right? Scattered light, blue sky, and so it gets brighter in the blue. But we also have this very sharp little feature right here is oxygen. That tells us that there's photosynthesis that's taking place on the surface of the Earth. We have these water vapor bands in our atmosphere, which tell us that probably there's liquid water on this planet. That's how we would interpret it. And then we also have methane in our atmosphere, which comes from bacteria that line our guts and the guts of our livestock. So if we can see a spectrum like this, right, then even though it's just a little dot with a few pixels across it, we'll be able to tell a lot about what those other worlds are like. In particular, we would look at this spectrum and we would say, gee, the combination of oxygen, carbon dioxide, which we see at other bands, and methane, this is atmospheric chemistry that's in disequilibrium. That means if all life on this planet went extinct, right, this oxygen band would go zoom, it would disappear in a time scale of 10,000 years. That's nothing, right? So the fact that it's here means that it's being replenished, right? It's not in equilibrium. There's something that's forcing oxygen into our atmosphere. With the James Webb Space Telescope, we will begin to look at the atmospheres. We were doing this already with Hubble and with Spitzer, I should say, but we'll have higher precision with the Webb telescope. And here's light coming from the star. We're over here looking with our spacecraft. These beams of light hit the surface of the planet, and they don't come to us, okay? That's why we have a transit. It looks dark. But the red wavelengths of light are penetrating through the atmosphere of the star. The blue wavelengths of light don't penetrate through as deeply. And all of this allows us to put together a spectrum. If we look at these red wavelengths, right, because they penetrate the atmosphere, the transit in red wavelengths is shallower than it is in blue wavelengths. So you put this all together, what you're collecting is the intensity of the atmosphere of the planet as a function of wavelength. That is a spectrum, right? And that is how we can, even crudely right now, be able to figure out what's going on with exoplanet atmospheres. So the James Webb Space Telescope, you see it here from the Visitor Center when it was at Goddard. It's actually shipped now. So James Webb will probe the atmospheres of large planets, but won't be able to reach Earth-like planets. So why not just go out and take a picture of them? This is not an artist's conception, like the other images I've been showing you. This is real image. These are real images of a star, HR 8799. It has 4 super Jupiters going around it. 1, 2, 3, 4, maybe. Sometimes it's hard to tell what are speckles. There we go. But you can see the ones that are orbiting, executing orbital motion, are planets. So all of these speckles, they look like these dots that could be, right? Is that a planet? Is that a planet? No, because it doesn't orbit over time, right? And so that's what we're looking for. These are planets that are, again, the size of Jupiter, are bigger and very far away from their host stars. They're not in the habitable zone. So what can we do next? I am the community co-chair on a NASA study for an instrument telescope, an observatory actually called LUVOIR. It's not French. It's the Large Ultraviolet Optical Infrared Telescope, right? We want to build a 15-meter telescope and put it in space and park it on the other side of the moon at the second Lagrange point, where, here we go. We'll just let it launch now. Put it up by that Tesla. Where we'll have a star shade and unfold. A lot of the technology for this space telescope is being developed with the James Webb Space Telescope. The launch vehicle, I'm sorry that actually this didn't turn out very bright, so I can see it on my computer, but it's not showing up very well here. We need a bigger fairing to lift a telescope this size off the ground, and so we are incredibly excited by the work that SpaceX is doing, right? And the private companies that are developing the capability of finally going to space. Here we come again. I think it does look brighter, doesn't it? Or is it just as it passes? That's just the sunlit side of the telescope. Okay. So we want to do a lot of astrophysics with this telescope. We want to be able to look at, here's a picture of Europa, one of the moons of Jupiter. This is data that was taken with the Hubble Space Telescope, and you can see that there are these bright jets because underneath the ice on Europa, there is water, liquid water, and there's cryovolcanism as the water comes out almost like a geyser. The picture with LUVOIR would look like this. So we would get incredible resolution, right, without sending a spacecraft there. We can resolve mountain features on the surface of Pluto. We can, in galaxies that right now are 12 megaparsec away, that's a huge distance, right? They're so far away that we can't resolve the stars in the galaxies with any telescope we have now. But LUVOIR would be able to actually resolve individual stars and study the dynamics of those galaxies. It would be an incredible instrument for looking for dark matter, for looking at black holes, and it would be a great instrument for looking for exoplanet atmospheres, which is my interest in it. Here's the challenge in taking an image of a star. So here is the sun at 10 parsecs, right? And at 1 astronomical unit, the distance of the Earth and the sun, the separation, the angular separation, is 1/10 of an arc second. Okay, you can divide up the sky into degrees, you can divide up a degree into 60 minutes, you can divide up a minute into 60 arc seconds, right? This is 0.1 arc seconds is the width of a human hair at a distance of 2 football fields, all right? But that's actually so that actually is the problem. But the bigger problem is it's right next to a very bright star. So we have to be clever about developing techniques, adaptive optics techniques and coronagraphs or star shades that can null out the light from the star. This is a simulation. So our team, our science, technology, and development team has built a lot of simulations to understand the science that we can do. Here's a simulation of the solar system. Now it's at 13 parsecs, so that's a little further than the slide before. And with a 12-meter telescope, where we're not sure yet what the size will be, and you can very, very clearly see, here's Venus, here's the pale blue dot of Carl Sagan's imagining, here's Jupiter, right? And you can get enough light from the planets, the individual planets, that you can take a spectrum and find out if there are biosignatures there. So we see this whole sort of the NASA swoosh, you know, which I hope will include W first, although it is currently not in the budget. We'll see what happens. And then some kind of an instrument like LUVOIR that will do incredible astrophysics, and finally look for biosignatures, look for methane and oxygen and ozone in the atmospheres of nearby stars. I think that the impact that these missions have on humanity is just incredible. Again, telling us about our place in space, telling us about our nearest neighbors, really, truly discovery missions which, you know, as we go out into the galaxy and begin to explore more, will give us the information that we need so we know what to do next. Okay, so I will end there, and I am delighted to take any questions that you all might have. There's a microphone that will go around. So
okay. Yeah. The transit method seems to require that the orbital plane of all the planets be exactly lined up with us.
Yeah.
And it seems like only a tiny percentage
of
stars would meet that requirement. How do you project or correct for that?
Yeah, so we believe that these, a good point, you know, if you imagine the sun is the size of a pea, then Mercury would be 12 inches away, infinitesimal dot, any tilt at all, and Mercury doesn't transit, right, from your view. And so it's, but the closer you put Mercury to that pea, right, the more likely, the higher the probability of a transit. So that's why Kepler found all of these planets that orbited very close to their host stars. We correct by assuming that these orbits are randomly oriented. And if that's correct, right, then even though we only see them over a few degrees from being coplanar, we can still make assumptions about what the population would be at all angles. And that's how we correct to get those numbers like 33% or 54% of stars have this type of planet. Okay, question up here.
Is there any looking into for dwarf planets like Eris or Ceres?
Yeah, you know, if we can get down to Earth, I think, then I will be happy. Looking for smaller things is just going to be that much harder. I think one interesting thing along that line is to look for moons, right, which could be about that size. And there, the best bet is probably with something like TESS or Kepler to try to find them. You might find evidence, literally the smoking gun for those small bodies by looking at in the far infrared. So looking for dust, because these things tend to collide. There tend to be collisions, and that puts up dust for some temporary amount of time. So an excess of infrared radiation would tell you that there are colliding bodies that are creating dust, and those are probably these small bodies like the ones that you mentioned.
Talked about the red dwarf stars that send off flares. Do they do that consistently throughout their whole life? And so the planet that's around them would most likely get bombarded too hard?
So they would definitely do that for the first, let's say, 5 to 10 billion years, right? And those are the formative years for young planets, right? Those are the years when the planets are outgassing and creating their atmospheres. And so if they lose that atmosphere at that point, it's hard to know how you could replenish it. You could replenish it from collisions, but it wouldn't be, it would be a hard thing to do. So even though it's true, you're right, that the M dwarf stars, as they age, the young stars are super active and running, blowing off all of these flares, and as they age, they slow down a bit, and then they might be better places for life. But again, if the atmosphere is gone, then that might make it tough. And I say that in complete humility that we actually have no idea, and we just have to go out and start looking. Question in the front?
In terms of the methods for discovering these exoplanets, which do you see to be most effective? The Doppler, or was the most efficient, the Doppler method or the transient?
Yeah, of course the Doppler, no, the transient method, there is just nothing like it. I mean, it just blew us away, right, with the discoveries from Kepler. But I am a little bit worried that if all we do are collect sizes of planets, that the amount of science that we can do is really limited. And so it's not so much that one is better, I would say more efficient in just sheer numbers, it's got to be transits, right? But in terms of characterizing the planets and doing science and understanding them, are they likely to have convection? Are they likely to have, molten iron cores with magnetic fields that protect their atmospheres? You need to have masses as well. And it just helps you to put together the whole picture. Yeah, thanks.
Is there more or less likelihood that the larger planets would have life, or are we making the assumption that it has to be the general size of Earth, or is it about the Goldilocks zone, or what's determining? I mean, might there be a super planet, Jupiter, like set up that could have life?
Yeah, so great question. And given that we know we have an example of one, it's always incredibly risky to try and extrapolate from that example, but when I come back to the solar system and think, all of the planets in our solar system are 4.5 billion years old, right? They've had plenty of opportunities to develop life if they were going to, and yet there's only one, the one that has water on it. right, that has developed life. That makes me think that there is something special about this planet. And I remember, you know, in 1999, we found the first multi-planet system. And at the time, the people who worked on extremophiles, the biologists said, you know, gee, wherever we look for when we find water on Earth, whether it's, you know, 5 kilometers under the surface of the Earth, or battery acid, you know, lakes, or whatever, wherever there's water, there's life. And we were just starting to realize how robust the planet formation process was too. And putting those together, I think, you know, it's probability, and in the absence of any knowledge, we just kind of go with what we know. Yeah.
The magnetic field of the Earth, which is rather weak, about half a Gauss, protects us from the solar wind. Even in our own planetary system, other planets have much stronger magnetic fields. So if you have a red dwarf that's really driven on stuff, are the planets around it? Have you done any studies? Well, what kind of magnetic field would be required such that it would deflect it?
That is a great question, actually. Yeah. As with a strong enough magnetic field, you could have this like invisible force field that buffers the planet and protects its atmosphere from stripping by the solar wind. I don't know of any studies. I think that's a brilliant question. Yeah, good possibility. I think the requirement is that there's some kind of a liquid metal core so that you have the turbulence you need to create a global magnetic field. I mean, that's kind of Venus's downfall, right? If Venus had a strong magnetic field, that might be a habitable world. So, yeah, great question.
Thank you so much for the fabulous talk, by the way. I thought that there was some kind of technique with interferometry. I'm guessing that coronagraph was part of that, and I thought they were already using interferometry where you block out the light of the sun, the star, to see exoplanets.
Yeah, so I was on one of the science teams for the Space Interferometry mission a while ago. Unfortunately, the funding was pulled from that mission. That would have been really exciting. But right now, the techniques that are being used are coronography, so blocking out the light of the star with adaptive optics imaging. Interferometry could be, I think, really interesting. The Europeans are planning to launch a mission to do this, but we don't really have anything right now that's observing a lot of planets. There are other techniques. So there's direct imaging, there's microlensing, there's interferometry.